adding inverses to stretches, reflections, and translations. It's like it totally could stand alone on its own self in any single unit if I wanted to. Like I could teach it in trig, I could teach it in terms and comps. It's a standalone lesson, right? So it's not like it's affected with the vertical stretch, the horizontal, and the translation. However, being that it's a standalone, people often forget about it. So they forget that it's on the test. They remember everything else, but don't remember this. So inverses are reflections in the line y equals x. Ooh, every time I wrote it down. This is called the identity line. This is annoying. Yeah. Called the identity line. Okay? It's the line y equals x, and it's the line that inverses reflect on. So remember when I told you when it reflects on the x-axis, the invariant points are on the x-axis. When it reflects on the y-axis, the invariant points are on the y-axis, because everything else flips, but that one stays the same. Inverses, it's that line y equals x. So the line y equals x is 0, 0, and then 1, 1, and then 2, 2, and then negative 1, negative 1, negative 2, negative 2. And it's this horizontal line. Okay? Now the reason why that's our reflector is, you should have brackets, but anyways, xy becomes yx in inverses. So in mapping, that means xy becomes yx. They just flip. You see how there's no negation sign on either of them? Like they don't flip in the negate or anything like that. They literally just flip. If the original point is 4, 2, the new point is 2, 4. That's it. Like it's not crazy. Okay? So the identity line is the line where y equals x. So it's where every y equals every x. We agree? So if I have the coordinate 2, 2, which means my x's and y's are the same, my y equals my x, and I flip that, it's 2, 2. Did it change? No, it's invariant. So that's why this line, this y equals x line, tells you how many invariant points there are. Like if I sketched a graph like this, the inverse graph would have 1, 2 invariant points, because here x and y are the same, and I would flip them, so it would be the same point. Here x and y are the same, if I flip them, it would be the same point. So if I ever give you a graph and ask you how many invariant points there are in inverse, just draw the line y equals x and count it out. So if I drew something like this, I would draw my identity line, whatever that may look like. I would need some actual. How many would this one have? 1, 2. And I would have to draw the line y equals x. Right? So it's not just 2, 2, and 3, 3, and negative 1, negative 1. It's 1.357 and 1.357. That's why you have to draw the whole line, right? Because that covers all the decimals, too. Because there's decimals where their x's and y's are the same as well. Okay. The other thing is, if my x becomes my y and my y becomes my x, then the domain of my original will become the y's of my inverse, correct? It'll become the range. And the range of my original, which are the y's, will become the x's, so it'll become the domain. So if I want the inverse, domain, and range, I don't even have to find the inverse. I can just find the domain and range of the original, and write the domain as the range, and the range is the domain. Because, for example, if my domain of my original was x such that x is greater than or equal to 4, x the noun and the reals, right? I told you inverses means x and y switch, correct? So these x's are going to become what? Y's. And when it's a y, what is it? Domain or range? Range. So this is the domain. When I flip those to y's, now it's the range of the inverse. So you actually don't even have to find the inverse graph if you have the original. You just find the domain and range of the original, swap the x's and y's, and you have the domain and range of the inverse. You know what I'm saying? Same thing. X-intercepts become y-intercepts, and y-intercepts become x-intercepts. But why is that? Make sure we're paying attention. So an x-intercept is a number and 0, correct? What does the inverse do? Takes that coordinate and flips it. So now it's going to be 0 and a number, which is actually the y-intercept. We agree? And then this one is a y-intercept, so it's 0 and a number. And it's going to become a number and 0, the next intercept. Okay. So here it says comparing y equals f of x to y equals f negative 1x, x equals f of y, or I could say a reflection in y equals x. All of these are 3 ways of saying, give me the inverse. Okay? If you haven't picked up a pencil or a pen yet, you probably should, because there's lots of things written down. So the graph of y equals f of x equals x minus 5 squared is shown. Well, we should show it. So x minus 5 squared is the x squared graph, moved 5 to the right. So 1, 2, 3, 4, 5. So it's going to be here and here, here and here, 4. That's y equals f of x. Now I told you that inverses x's and y's flip, correct? So let's, on the right-hand side, write out what the coordinates are from that graph, from the original. So from the original, my coordinates are 2 and 9, and 3 and 4, 4 and 1, 5 and 0, 6 and 1, 7 and 4, 8 and 9. And these are from y equals f of x. And then we're going to get the coordinates for y equals f negative 1x, which is the inverse, right? So your other mapping is kind of harder to do because you have to do like flipping things, keeping things, all the different things. Those are harder to do. But inverses aren't harder to do. You literally take the coordinate and flip it, redraw it. This lesson people find really hard. It's literally just this to this. xy becomes yx. If you can get that, then it's easy. Domain becomes range, range becomes domain, x-intercept, y-intercept, x-intercept, right? So we're not like trying to remember to flip or keep. It's way easier. So 2, 9 is going to become 9, 2. And 3, 4 is going to become 4, 3. And 4, 1 is going to become 1, 4. Five, 0 is going to become 0, 5. 6, 1 is going to become 1, 6. 7, 4 is going to become 4, 7. 8, 9 is going to become 9, 8. And then you have arrows on the end. And these are reflecting on the identity line. I'm going to draw the identity line as a dashed line. So it goes through all of the 1, 1, 2, 2, 3, 3, 4, 4, these. And I'm drawing it as a dashed line so that we know it's not actually part of the graph. So look, where do these two graphs, where do they cross? Here and here. They're invariant at those two spots because that's the identity line, correct? So this line here, that coordinate is invariant. And this coordinate is invariant. We're going to talk about the domain and range too. So the black graph is the original. And I'm going to give the domain and range of the original. So original. What is the domain of that black quadratic? X such that X is now in the reals. So in set notation, it's X such that X is now in the reals. In interval notation, it's negative infinity to positive infinity. And then your range, what's your range in set notation for the black graph? Yeah, y such that y is greater than or equal to 0. Y is now in the reals. Make sure you use a comma and not a semicolon. It's just a comma here. And then in set notation, from 0 to infinity. What it's equal to, so I have to do a square bracket to infinity round bracket. Now, I didn't even need to draw the blue graph, and I could have given the domain and range of it. Because it's just literally these ones, y's become x's and x's become y's. So if I do the inverse, my domain is my range of my original with x's, because these y's are going to become x's, right? So it's this exact range, but with x's. So x such that x is greater than or equal to 0, x is now in the reals. In interval notation, it's just exactly the same, 0 to infinity. So I start at 0 and then go to the positive. Now my range is my domain. So if my domain is xer, my range is going to be yer, because the x is become y, right? And my interval notation stays the same, negative infinity to positive. We marked the invariant points on there already. How does the graph of y equals f negative 1x compare to the graph of y equals f of x? It's an inverse, or we can say a reflection in the identity line. Y equals x. So this is the graph of y equals f of x. We want to draw the graph of y equals f negative x. If we're moving a graph, we're moving coordinates. If we move a coordinate or coordinates we use mapping every time. And the mapping for these are the easy ones. Because our mapping is just x, y becomes what? yx. Right? So you're literally going to take the coordinates off that graph, flip them, redraw it. And they'll make it reflect in the identity line. So the ones I would use, pretend this one's at -40, because my board is not printing them up. -40, -1 and 4, and then 1, 0. I want you to sketch the new one, and then I want this domain range x-intercept, y-intercept of the inverse. You could do the original first and then convert it if you want to, but go. The other one I probably should have pulled was 0, 2. Okay, so these are going to become 0 and -4. When my x is 0, is that an x-intercept or a y-intercept? This is a y-intercept, right? X equals 0 when it's a y-intercept. So this was an x-intercept, correct? It is now a y-intercept. Okay, so now I have 0 and -4. See, look, it's on the y-axis. That's a y-intercept. We agree? Okay, then we have -1, 4. That's going to become 4, -1. That's just a coordinate. So we go to 4 and -1. We sketch that way. 0, 2 is going to become 2, 0. So this is a y-intercept. It's now going to become a x-intercept. And then this is an x-intercept. It's now going to become a y-intercept. Okay, the original domain and range are easier to find, so the original, we'll call it the OG. Do not write OG on your diploma. I get people doing it on the unit exams all the time. OG is a joke. OG is not original. Might be in your terms. You don't know who's marking it for you. So the original is the domain is the black graph, and it goes like this out for life, right? Parabolas do that too. They're just rounded, but it doesn't change the fact that it goes from here and all the way up. So every x value in the world exists on it. So the domain is XER. So those x's become y's, so that's going to be the range. Y such that y is an element of the reals. And then the range of the original, it's 1, 2, 3, 4, or less than it, right? The highest it goes to is 4 or less. So it's going to be y such that y is less than or equal to 4, comma, y is now in the reals. Please use a comma and not a semicolon. Comma. So that's going to become x's. So that's going to be my domain. X such that x is less than or equal to 4. X is now in the reals. And then we have to label the invariant points. The easiest way to label it is to literally sketch that identity line. So 0, 0, 1, 1, 2, 2. So like this. Right? Well, it crosses here, doesn't it? So that is this right here is my invariant point. Okay, domain becomes range, range becomes domain, x-intercept, y-intercept, y-intercept, x-intercept. Did I need to draw this purple graph at all unless it asked me to draw it? No, because I could base everything off of here, right? My y-intercept became x, my x became a y. My domain became a range became a domain. The only reason why I have to draw the graph is if I physically asked to draw the graph. Even the invariant point would have popped out without the purple graph because it would be where this black graph crossed through the identity line, right? I didn't need the purple graph. Okay? All right. Try again. These are of the inverse. I'm going to do this without drawing the graph. Prove a point. Okay. The domain of the original, what is it? From what x to 1x? Negative 6 to what? 7. So if I do it in interval, it's negative 6 to 7. Square brackets because those are closed dots, right? So it equals them. In set notation, that would be x such that negative 6 is less than or equal to x is less than or equal to 7. And some people fight me on this because they don't realize, they say, like, how can one be less than and one be greater than, and they're in the same direction? That makes no sense. It's because when you were little, less than always was closed from the left to the right, and greater than was always open from the left to the right, and that's not real. It's from where the variable is. So if we look at this, we're working this way to go towards the negative 6, correct? And it's open to the x, yes? So that means greater than. Yeah?
Does it matter if it's like reverse, if it's still the same thing? Like if I put 7 is greater than or equal to 5, or just greater than or equal to negative 6?
Always low to high. Yeah. And then this one is x is less than or equal to 7 because it's close to it, right? And then we have x and now in the reals. So I don't know why I have that dot. I dropped my pen, sorry. I may have the domain of the original, but now what do I have of the inverse? The range. So I can immediately go here and go negative 6, 7. Like it would be the exact same in interval, correct? And the range it would be y such that y, oops, that's a lie. Y such that negative 6 is less than or equal to y, is less than or equal to 7, y is an element of reals. The reason why I'm not drawing the graph is because you already have it drawn in front of you. I'm just showing you that I can do this without drawing it. Now, if I said sketch the graph the inverse and you don't do it, you just didn't do what's asked, so then you'd be in trouble, right? Okay, range of the original. Now I'm going from negative 3 to 1, 2, 3, 4, 5, 6. Negative 3 to 6. Or y such that negative 3 is less than or equal to y, less than or equal to 6. Y is now in the reals. So that's the range of the original. So that would be the domain of my inverse. Those y's become x's. X such that negative 3 is less than or equal to x, less than or equal to 6. X is now in the reals. And then it would be from negative 3 to 6. Okay, now I'm going to pull my y-intercept off of here. My y-intercept is 0, 4. So that's going to become 4, 0, which is my x-intercept, yes? My x-intercepts are negative 6, 0 and 7, 0. And they're going to become 0, negative 6, which is a y-intercept, and 0, 7, which is a y-intercept. And then I have to label the invariant point. Do I need to draw the graph so that I can find out where they intersect and sketch it that way? No. I can just go through 0, 0, 1, 1, 2, 2, 3, 3, this way. This way. That's my y equals x line, and it crosses here. So that's my invariant point. So you see how I didn't draw the new graph at all, and I still got all the information? All right. So, what I'm going to do for the last little bit is tomorrow we're going to finish up. I have one outcome that I still have to go through with you. The last outcome I have to go through with you in transformations is I'm going to give you a graph that when you sketch it, so a parabola, let's say, when you sketch a parabola, it actually turns sideways like this, right? It's no longer a function. If I draw a vertical line test through it, it does not pass. It crosses more than once. So the outcome that they make us teach you is how can I restrict my original graph so that when I draw it, it will be a function. It will pass the vertical line test. So for example, if I had a parabola and I took this arm off and I redrew it here, it would now pass, right? It has one arm. If I took this arm off and I redrew this one, it would pass, right? So it's cutting off the domain. So you would take either x is less than or equal to, say this was centered at 0, 0. X is less than or equal to 0, I would get this one. X is greater than or equal to 0, I get this one. And then it would pass when I draw. So that's our outcome for tomorrow. So I'm going to grab the hand ends and I'll give you the last part of the class to start working on it.